Tonight's speaker, Dr. Joe Biasi, is an assistant professor in the Geology and Geophysics Department of the University of Wyoming. He specializes in volcanoes, ore deposits, and all other rock-related topics. Before coming to Wyoming, he did his postdoc in Dartmouth. He got his undergraduate degree at the University of Indiana, and then his master's and his PhD at Caltech. He has authored numerous papers ranging on topics from paleontology in Antarctica to plate tectonics in Alaska. At the University of Wyoming, Joe runs the Mineral Exploration and Deposit Analysis Lab, METAL. All the labs have very clever names, which helps to prepare students for successful careers in earth science. Please join me in welcoming Dr. Biasi.
Thanks. Thanks for the introduction. Thanks for coming, everybody. Can we hear me okay? We're okay? Okay, you can see the title slide. Let's move on. So I said, let's move on. There we go. So today, this talk's going to be in 4 parts. Part 1 is about the future. The middle 2 parts are about how I'm trying to solve some of the problems, help solve some of the problems associated that are coming up, and then how we're going to prepare for the future. It sounds vague right now, intentionally. We'll get there. So let's see. Part 1, an uncertain future. This graph is one of the most important graphs in human history. On the y-axis, we have the population of people on Earth. On the x-axis, we have time. And it starts at 10,000 BC, the dawn of civilization, the rise of agriculture, things like that. And you can see that for most of human history, the human population was pretty stable, very slowly increasing. And then right around the Industrial Revolution, it also coincided with an agricultural revolution and the invention of fertilizer. And with that, the human population exploded, basically. It's gone more than exponential, right? And associated with this, some things have gotten better, and some things, there's some problems that have arisen from this. So not that long ago, people didn't live the way we live today, right? The vast majority of people, 98% or something like that, were farming. They were living agrarian, pastoral lifestyles or something like that. And their resource needs, by extension, were pretty immediate and not that complicated, right? Here, if we break it down to literal elements in the periodic table, you needed very few elements. You needed carbon, which is most of the stuff you ate. You needed salt, and you needed water, basically. Don't even highlight oxygen because the air is free, right? Your variety of needs isn't that great. If we fast forward to today, right, things are very different. We have replaced the natural world with jungles of our own creation, right? And as a result, though, when you try and replicate a habitat for people alone, you have to use almost all the elements that nature had already given you in the first place. In order for modern society to continue running, you need all of these elements, basically. Some of them not in great amounts, some of them in small amounts, but you still need them. So I've left the green ones highlighted from before. Now, to make society continue to function, we need all of the other ones. And all these other ones ultimately come from the ground. They come from mining. They don't grow very well. They don't grow on trees like carbon does, right? So this can cause some headaches, right? Associated with that, not only do you need a greater variety of elements to make society function, but our material demands have been increasing, ever increasing. High technology does not reduce our dependence on like raw material. It only adds more, right? A Kindle, as it turns out, takes way more resources to make than a book. There's no way around it, right? So that's just one minor example. This graph only goes up to the year 2000. It's only going up higher from there. Our material needs keep increasing, basically. And so this is one of the major problems is how do we keep all these people going? How do we keep civilization going? How do we bring people out of poverty and into civilization when doing so requires ever more and more resources, basically? So one of the problems we're going to discuss today is resource needs and scarcity, basically. There's another problem. Here is a map of all the volcanoes, all the recently active volcanoes. This is Holocene to present, which is about 12,000 years ago to the present. around the world. And here is a chart of how many people live near a volcano over time. So on the x-axis, we have literal distance that you live from the volcano. And on the y-axis, we have how many people live within that distance. Then the little lines are just colored by year. And you can see from 1975 to 2015, the number of people living near, let's say, a volcano has doubled. And that's because roughly the number of people on Earth has doubled since that time. This isn't just a volcano problem, it also applies to people living in earthquake-prone areas or landslide-prone areas. You guys know a little bit about that, right? As you get more and more people, they need to live somewhere. The best places to live are crowded, so they move to places that are less crowded, which are often more hazardous, right? Earthquakes, volcanoes, landslides, hurricane, same problem sort of persists. Here's a great example. The island of Java, which is just right here in Indonesia. The island of Java is about half the size of Wyoming, something like that. And it is home to 156.4 million people. 156.4 million people. These people are overwhelmingly pretty poor. Their average GDP per capita per year is about $5,000. There's quite a few people in Jackson who make that much off of passive income from investments every day, right? But this is GDP per capita per year. It's not a very wealthy place, right? And on top of having 156.4 million people, they have 36 active volcanoes on the island of Java. The capital of Indonesia, Jakarta, is right here. The darker the green, the more people live there. The capital is right here within a volcanic hazard area. There's people that literally live completely surrounded by volcanoes on Java, for example. Indonesia doesn't have a lot of money. Their people are poor. They don't have a volcano monitoring program. None of these volcanoes are monitored at all. Singapore does a little bit for them, but they don't monitor everything that they probably should or could, right? This doesn't only apply to faraway places. Does anyone recognize this place, right? You guys live within 100 kilometers of an active volcano, right? If we go back to my chart from earlier, you guys are on this chart. All the people of Jackson are on this chart. And if you moved here since 1965 or 1975, then you have totally added to the lines, right? You've added to this increase of people that live near volcanic hazards, right? So the other thing I'm going to talk about in this talk is greater exposure to natural hazards, another result of just having more people on Earth, basically. So let's start with the natural hazards. So I'm going to talk about a little preamble about how people monitor volcanoes. Volcanoes are the hazards I really care about. Let's say you have a volcano and you want to monitor it. You have people living nearby and you want to figure out, okay, when's this thing going to erupt? Can I get some forewarning? The oldest way to do that is by sight. You just go take a look at it every day and see if it looks any different. This is the cheapest method, but it also is the least accurate in that sometimes you don't notice anything till it's already erupting, right? People also try earthquakes. Sometimes when magma is moving closer to the surface, it makes little earthquakes. You can try and record those earthquakes or try and notice an increase in activity. Some people monitor gas. Most volcanoes emit gases. You guys know about this from Yellowstone, right? And sometimes when magma moves around, it'll emit more gas or emit gases of different ratios, different compositions, or something like that. A popular one these days is GPS or deformation. Sometimes if a magma is coming closer to the surface, it might bulge the surface out a little bit, displace the surface a little bit. And if you have a very accurate GPS, you can detect that. You can detect that. And then the gold standard is gravity, is measuring the pull of gravity, which is not very intuitive. So I'm going to talk about it a little bit because it's actually important. So let's say we have a volcano, right? And we have a magma body underneath the volcano. As it turns out, magma is not very dense. It's way less dense than the rocks. It's because magma is a liquid, and most liquids are less dense than solids, basically. So if you were to walk across this volcano and literally measure the pull of gravity, you will notice a low right above your volcano. And that's because there's literally less mass below you. Remember, the pull of gravity is proportional to mass. We're going back to high school physics here, right? There's literally less mass to pull you down underneath the volcano because the magma is less dense, doesn't weigh as much. So people notice that on a lot of volcanoes, you get these gravity lows. What happens, right? If magma is less dense, but also magma is not stationary. What if you come back next year and something's changed? Let's say you've had more magma come in, or magma's gotten closer to the surface or something like that. Well, if you do your transect again, you'll notice that the pull of gravity has changed from year to year. Does this sort of make sense? This is the fundamental how gravity monitoring works, basically. So you monitor changing signals in the literal pull of gravity, and you can figure out if magma's been moving around beneath you. You can figure out if it's getting closer to you or farther away, or stuff like that. So gravity is the gold standard. I put it in gold. Isn't that cute, right? The gold standard. It is also the least common way to do it. And to explain that, we need to get into costs. Okay, sight is free. Isn't that nice? Unless you use a satellite, then the costs are astronomical. Get it? Anyway. A seismometer measures earthquakes up here in the top left. A cheap one's going to run you about $1,000. An expensive one, about $10,000 for a volcano station at least. They get more expensive, but on volcanoes, you typically don't spend more than $10K on a seismometer. Gas measurement system, about $10,000 to $100,000 for your gas measurement setup. A GPS station, your handheld GPS is not accurate enough. Your phone is not accurate enough. You need a very accurate system. That'll also run you about $10,000 to $100,000 for one station. Ideally, you have 20. Same with seismometers. Ideally, you have about 20 for a decently sized volcano. One gravimeter is $400,000 minimum. Most of them these days are about $600,000. It's $400,000 if you build it yourself, and it takes a year to do that, right? And keep in mind that if your volcano erupts, you could lose all of your instruments and all that money is down the drain, right? So this gets expensive very quickly. Here's a great example. Here's Yellowstone. Yellowstone is monitored by the US Geological Survey. They have the Yellowstone Volcano Observatory. These are their instruments that they have on Yellowstone. They have some cameras, that's part of SITE, right? They have 29 GPS stations, it's a pretty good network. They have 35 seismometers, right? You'll notice they don't even have a gravimeter here. They can't afford it, right? There's no gravity monitoring, the gold standard, at Yellowstone. That's kind of not true. The USGS has 2 of them, and they just like drive them around the Western US all year. So they'll monitor Rainier for a month, and then they'll monitor St. Helens for a month, and then they'll monitor Yellowstone for a month. But we don't have a permanent one at Yellowstone. We can't afford it. If something actually blows, then you lose all the money, basically, right? So we want gravity, but cheaper. That, in a perfect world, we would get gravity, but cheaper. And that's what I had set out to do when I learned how crazy expensive all this stuff was. I'm like, there's got to be a cheaper way to do this. So that's what I'm going to talk about. So as it turns out, there's a very similar geophysical signal that you can measure, something very similar to gravity, that is actually way cheaper to measure. And that is magnetics. That's magnetics. Magnetic fields and gravitational fields are pretty similar geophysically. And the concepts are very similar. Rocks, as it turns out, are very magnetic. They have all these little magnetic minerals in them, mostly magnetite. They're very magnetic. Magmas are not magnetic at all. They're too hot to be magnetic. No magnetic field's really stable in a magma due to some complicated like atomic scale physics things. The point is, if you go to a volcano and you do your transect, but this time you're measuring the magnetic field, you also see a low. You also see a low. People had already noticed this. My idea was, well, what if we go back another year and do our little transect again? As the magma changes, you should see a change in the magnetic signal too. And the advantage here would be that the magnetics are way easier to measure, basically. I'll get into prices in a few slides. But it's the same concept as gravity, just you're measuring magnetics instead, basically the magnetic field. Okay, I wrote a paper basically modeling a bunch of volcanoes and showing like theoretically this should work. And then we went out and actually did it on an underwater volcano, Axial Seamount. It's off the coast of Oregon. It's super active, that's why we picked that place. And every year we made a little magnetic map of the volcano. And every year that magnetic map like appreciably changed every year as the magma was moving around and stuff like that. So as a proof of concept, we're still improving this concept a few years later. Here's another example. This is Askja volcano. It's right there in the middle of Iceland, and it's a very, very large volcano. It forms this huge caldera. It's not quite as big as Yellowstone, but it's sort of in the same league as Yellowstone, basically. It erupted in 1961, and for 60 years, it was deflating. What that means is that the magma, whatever magma was underneath it, was going somewhere else. The ground was caving in. 3 years ago, it began rapidly reinflating. Magma was rapidly coming back to the volcano, right? So this is a chart. These are GPS stations. On the y-axis is up. This is the GPS station getting pushed up by the magma below it versus time. And you can see that from 2021 to about mid-2023, it was ascending at what geologists would call a very rapid rate, right? A very rapid rate. Sometime in fall of 23, it leveled off a bit. You can see all these stations, their rate of uplift leveled off a bit. That'll be relevant in a couple slides. We were a little late to the party. We deployed our magnetometers, the things that measure magnetic fields, about a month or two before that leveling off happened. So we caught the end of the rapid uplift, and then the rest of the year was this leveling off part. We'll get to it in a second. We tried a few different strategies because we weren't sure what would be good. One is we did an aeromag survey. This is where you strap your instrument, your magnetometer, to a drone, and you let the drone fly around and cover a bunch of area, so you don't have to walk around, basically. It's very tough terrain. This is the most expensive because drones are expensive, and drones crash a lot, right? As it turns out. The weather in Iceland is not very good, right? Another thing we tried is a ground-based survey. It's where you strap your instrument to your back and just walk the same line every year. You don't get as much spatial coverage, but you're not going to like destroy your instrument by crashing it. We also deployed fixed stations that measure year-round. This is fine as in fine resolution, not like, oh, it's just fine, right? Fine resolution magnetometers. So these things are pretty high-end. They're about $1,000 each, and they will measure all year round, but they don't walk around. They just measure like one spot all year. And then the other one that we tried that I'm most excited about is what we call a coarse resolution magnetometer. These ones are $100. They're $100. If they work out, they will replace an instrument that costs $400,000, right? So it was worth a try, right? They're so cheap, you can densify your network, you can throw a lot more of them out, and they just fit in this little Pelican case or whatever, right? I make them myself. It's not a very complicated instrument at the moment. So here's some examples. We have this fine station way off the volcano. This is our base station. You need a base station, as it turns out, because the magnetic field you measure is not just affected by magma below you. It's mostly affected by space weather. You guys remember those like big aurora back in May or something like that? That actually gets picked up by the instrument. That's what this big spike is right here, for example. So you need to account for that when you're trying to figure out, well, what's my actual signal from the magma, not from this background noise? So we have a base station out here. I'll compare it to data from this station right in the middle of the caldera here, right? You can already see they're a little different, right? The most basic way to process these data is you just subtract the base station, subtract the noise from the station you care about, from the signal, right? So you just subtract your background space weather stuff away, and you should get the signal from the magma at the most basic level. So here's what happens when you subtract the base station from this caldera station here. These are the differences. You'll notice they're not exactly the same, right? There's clearly some change between this station and this station. We were late to the party. Whatever was happening right before we deployed, we had a huge drop in signal for the first like month or two, and then it leveled off. As magma gets closer, as this non-magnetic stuff gets closer to our sensor, we expect a drop in signal. So it looked like the magma was getting closer and closer to the sensor, and then it leveled off, right? As it turns out, the timing where we got the change in slope from big drop to leveling off perfectly corresponds to this change in slope, the timing of the uplift. Right when the uplift stopped, our drop in signal also stopped, right? So we have pretty good agreement between these two methods, the GPS method and the magnetometer method. They're both showing that the magma has stopped coming farther towards the surface, basically. For the coarse magnetometers, I want to talk a little bit about them. They're about $100. I make them myself in my lab at the University of Wyoming, basically. 4 AA batteries will power them for a decade. That's what I spent the full first year working on, was getting battery life to be as good as possible. That's basically the shelf life of the battery at this point. You can add telemetry, which is just a fancy, smart sounding way of saying satellite links or cell phone links. That's what drives the price up to about $300 if you want that. Otherwise, you got to collect it off the SD card once a year. You have to show up and collect the data off your SD card. They're not a final product yet. They're not ready for sale, for proper sale or anything like that. We go through a different version every month. We're always working on improving them, basically. Every time we collect data or every time we deploy them, we learn some new things and improve the design. But one day they will be ready and they could sell for like $100, for example. So let's compare this with gravity for a second. What's the pros of using magnetics? One is that it's way less expensive. That's the main pro. It's just way, way, way less expensive. We're talking a $100 instrument versus a $400,000 instrument, right? The instruments are very durable. My $100 instruments can just be thrown out of a helicopter if you want. The gravimeters need to be perfectly level and perfectly stable, and you need to pour a concrete pad for them, right? My instruments are sensitive to hydrothermal systems, which if you're worried about hydrothermal hazards like things in Yellowstone, that's very useful. A con is that they're sensitive to hydrothermal systems. And if you only care about magma, it's unnecessary noise, right? They're also affected by space weather, these auroras and stuff like that, which can be hard to correct for. This is a brand new technique. Best practices have not been developed yet. I'm learning all this on the fly. And therefore, the supporting industry is not yet developed. You can buy the high-end magnetometers off the shelf. You have to figure out how to weatherproof them and snowproof them. The low-end ones, I'm just making myself, and I'm learning as I go. So I am the only one doing that. Current deployments, we have 2 in the Aleutians, up here. We have 2 in Iceland. We have 1 in Chile. We have 1 in Ecuador. You'll notice a conspicuous lack of deployments in the Western US. I'm actively working on that, right? Actively working on that. And then the final slide on this part is, who is this for? Like, who is this technique actually for? In my mind, if you were to put these instruments on Mount St. Helens or on Kilauea, you wouldn't learn anything because they already have every other instrument out there. They already have gravity. They already have all the seismometers, all the GPS. In my mind, these are for countries with too many volcanoes and not enough money to monitor them. That's where I think these would be most useful. We're talking the Indonesias of the world, the Philippines of the world. Not a lot of money, hundreds of volcanoes to monitor. So at $100 an instrument, you put them on every volcano and they're your first line of defense. And you use their data to better allocate the more expensive instruments that these countries don't have a lot of, right? A whole country might only have 20 seismometers. You'd use mine to figure out where you're going to put those 20, for example, in their volcano monitoring program. That's part 1, right? We talked about some hazard stuff. I'm going to transition here to the resource scarcity thing. We're going to do a hard pivot. It's basically 2 halves of a talk here. I don't know, what do you guys normally do?
Normally, we just do them all at the end.
I'll take a question or 2, sure.
I thought an oil field person carrying a gravitometer was $400,000.
Yeah, so they sell cheaper ones that are around 120K or something like that. Yeah, so the question was, I saw oil field people carrying around gravimeters that were not $400,000, and they do sell cheaper ones that are about 120K or something like that. Those ones are not sensitive enough for volcanology, for volcano monitoring, basically. And they cannot sit outside for a whole year either. They can't get wet. They can't get snow. They can't handle a snow load or anything like that, which most volcanoes have a lot of snow on them, as it turns out. So when you get to something that has to sit around for a whole year, It has to stay perfectly leveled, and it has to have an auto leveling system. And you need to add all the waterproofing for it. You need to add the structural rigidity so it can handle 20 feet of snow. And these things get complicated, and that's what drives up the price a lot. And it needs to be more sensitive. So that's why it gets to $400,000 for a volcanology one. Yeah. I'll move on for now. We can take more questions at the end. So let's talk about the other problem I'm dealing with, which is resource needs and scarcity. Let's talk about critical minerals for a second. What in the world am I talking about here? Let's go back to New York City for a second here, right? Today, we use almost every element of the periodic table to make modern society function. Not all of these elements are easily available or readily available or have a consistent supply. And most of them, our suppliers are not in the US, they're other countries, right? And we need more and more of them as time goes on. The reason why it's very hard to get these things in the US is that starting a mine, operating a mine, and closing a mine in the United States is very, very hard. It's very hard. Here on the right, I have the life cycles, the parts of a mine. You start by finding a deposit. You figure out if it's actually feasible, if it's actually going to make you money. Then you mine it. Then you close it. All of these things are hard in the US. In some countries where they don't have environmental protections or human rights, and all you need is the favor of the dear leader, these things are easy. All you need is someone to say, yeah, sure, right? But in the US, it's a lot harder to do. So as a result, we have this problem, which we call critical minerals. These are mostly elements, actually, not minerals. These are elements or minerals that we import from countries that are not necessarily reliable suppliers to the US. So these are all elements that we need for national defense or for the energy grid or something like that, that are imported from countries that could cut us off at any moment and very well might. We're talking the Chinas of the world, the Russias of the world, stuff like that. If we're entirely dependent on Canada for a mineral, it doesn't really make it on the critical minerals list. Canada is a reliable partner, for example. So the USGS has their list of 50 critical minerals. And you'll notice on this, all these ones on the right, we have 100% import reliance. 100%. We do not make a single bit of this in the US. And if we don't have any, let's say, europium left, we cannot make any more fighter jets or aircraft carriers or anything like that, right? So if the Chinese ever cut off our europium supply, we would not be able to make those things, for example. The Department of Energy has a different list because why would the government agree with itself, right? On the y-axis, we have reliance or importance to energy. On the x-axis, we have supply risk, right? A lot of these are obscure elements that we don't deal with every day, but most of them are used in high technology or military or stuff like that, right? Fighter jets, aircraft carriers, semiconductors, computer chips, that sort of stuff, right? Another compounding problem is that we don't know how much of most of these things are even out there. This circle in the center are most of the metals that people actually mine. People start gold mines, people start iron mines. That's what I mean by that. Most of those other weird metals that are on the critical minerals list are byproducts of these mines. So for example, there's not a single indium mine in the world. Not a single one. Indium is most commonly a byproduct. They find it on accident when they're mining copper. So on paper, we only have 2 months of indium left in the world, right? Only 2 months of supply left. That's not really true. We keep accidentally finding more when we mine copper, basically, in Chile, right? So we're not actually sure if when we're going to run out of a lot of these things in the other countries or in this country because they're byproducts. They're not actually very well characterized. Their resources are not very well estimated. When it comes to mining in the US, we don't mine a whole lot. Most of our mining is concentrated in the Western US, Missouri, Michigan, and Minnesota. Texas is only red because of aggregate. This is crushed stone, right? That's why Texas is in the red. All these other eastern states only have a color because of aggregate, because of crushed stone. Actual metal mining, critical mineral mining is almost exclusively done in the Western US, basically, Western US and Alaska. Our total industry is about 105 billion a year, which is a paltry sum compared to some other countries, basically. Speaking of other countries, here's where we import most of our critical minerals. you'd see our two largest trade partners are Canada and China. Canada's fine. Canada's a reliable partner. They live in fear of us sometimes that we could invade at any point, right? China, on the other hand, not a reliable trading partner at all, right? Russia, we are actually dependent on Russia for a whole bunch of our critical minerals. They have not cut us off yet. It'll be interesting if they do, right? Brazil, not as reliable as we'd like. South Africa, not as reliable as we'd like. If we're reliant on Russia, let's say for chromium imports, that might get chromium put on the critical minerals list, right? It's essential to our society, but we don't really make it. And it comes from a country that's not reliable. Congress. Ooh, Congress, right? Congress is aware of this issue. And unlike most things, they're actually trying to do something about it, which is, I know, a shocker, right? A few years ago, during the Trump administration, they funded the Earth MRI project. This is Mapping Resource Initiative. This is a big pot of money for the US Geological Survey to map and gather geophysical data for a big swath of the country. And what they're trying to do is get the background data before the exploration stage, the like base level geology that will actually let you do exploration. So they're collecting a lot of aeromagnetic data, which we talked about earlier in the talk, airborne radiation data, all these other things. They're very active in southern Wyoming right now. They've been flying all over southern Wyoming gathering these data, basically. You can tell that's an actually good idea because when the Biden administration came in, they threw even more money at it. They didn't cancel it, right? They threw even more money at this. Congress did not just fund Earth MRI and call it done. Since then, they've been introducing all these critical mineral bills, some of which are actually passing or have actually passed. Almost all the critical mineral bills that get introduced are bipartisan. Senator Barrasso of Wyoming has sponsored quite a few of them, actually. He's very into this, right? It's a bipartisan issue that's getting bipartisan votes, basically. Not every bill makes it out of committee or passes, but it's a thing people are constantly doing, and some of them are getting passed, basically. It's an actually serious issue, and Congress is taking it seriously, in part because it directly affects national defense, right? Which is a good way to actually get something done. All the money in the world will not necessarily solve this problem, because there's another problem that we have to deal with on top of this, and that has to do with this chart. This is enrollment in undergrad geoscience degrees over time. On the y-axis, we have the total number. On the x-axis, we have the year, right? You guys can see we peaked around 1980, something like that, early 80s. Hiring for geoscience jobs in the 80s wasn't that great. The oil companies were not hiring at the rate they were previously. And so our enrollment declined dramatically. It's been slowly rebuilding, but it declined during COVID and actually hasn't recovered post-COVID. A lot of these people in this cohort went into environmental fields instead of oil and gas. Some of them went into oil and gas. A lot of these people went into oil and gas and mining. This peak, these cohorts of people, some of you were part of it, are retiring or have retired. And they're not really getting replaced. We haven't been graduating enough geoscience undergrads to replace them. So this chart shows that currently there's about 300,000 geoscientists. By 2029, we'll graduate another 25K, and then another 130 will have retired by then. That's the talent deficit. This chart foolishly says filled by substitution and innovation, which is not possible for like a quarter of the entire workforce, right? In geology. It's not how that works. You can't AI your way through geology, as it turns out, right? If you're one of these new grads, if you have a grandchild or something like that, this is a good time to get a geology degree. I've had plenty of mining company executives tell me they'll hire anyone with a degree and a pulse, right? A degree and a pulse. Yeah. So why would they do that? Why would they hire anyone with a degree and a pulse? Let's take an example from the world of copper. Here's projected growth in copper consumption through 2040. Growth in copper consumption, not current copper consumption. The biggest field is green consumption. This is wind and solar. Even if you think that's a lot of BS and that's not going to catch on, right? All the other fields are also growing quite dramatically, right? There's an undeniable need for more and more copper as time goes on, as we electrify our world, right? So let's put this into perspective. This cube is 700 million tons of copper, which is all the copper that we have ever mined in all of human history, to our best guess. They think by 2050, 2060, we will need to mine 1.4 billion more tons of copper. We will need to mine more copper than we ever have in all of human history. If you get rid of the green energy part, we still would need to mine 800 billion tons of copper, which is still more than we ever have in all of human history, in order to meet demand. You guys all have stocks, you all have investments. This is not priced into the market. The NVIDIA stock this last year, it is the availability of raw resources to actually make computer chips is not priced into these stocks at all. All of our current economic models assume endless growth that is not rate limited by by the earth itself, right? To actually make our economy function, we need to find all this stuff. We need to find all of it, right? At the same time, the best copper has been mined away already. This is copper grades of new deposits found over time. Doesn't matter what country you're in. The best, most rich copper deposits are all already found, already mined out. There will not be another Butte, Montana. There will not be another, the best are already gone. So you need to find more than ever, and the grades you have to work with, the literal richness of the copper that you can find is getting worse than ever. Can you see why the copper companies are hiring anyone with a pulse, right? They need all the help they can get, basically. Some countries have gotten the memo and they're trying to rise to the demand. Chile is a great example. They have totally ramped up their copper production as demand has gone up. All these other countries have also ramped up some. The US, on the other hand, which is the blue curve, we went down in the 2000s and we've leveled off since then, basically. We've not been ramping up to meet demand, in part because it's very hard to open a mine in the US, right? This is not exclusively a copper problem. Actually, the problem's worse with other commodities. Nickel is a great example, which is shown here. Nickel, we're going to have to mine more of that than we ever have before. We're going to have to mine more cobalt than we ever have before. It's a continuing problem, basically. And this is why it's a good time to be in geology. They're going to need more geologists than ever to help find all this stuff, basically. So how am I going to prepare my students for this future? For our future where mining companies will hire them, basically. So at WYO, I run the metal group, which is mineral exploration and deposit analysis. Unlike some of my colleagues, my number one goal is student success. You would think that's every professor's goal, but that is not. The other economic geology professors, the other mining professors at other institutions, yes, they want their students to be successful, but they're mostly judged by how many grants they pull in, how many papers they publish. Their universities have been taken over by accountants. And the student success is secondary to getting your grants and your papers out. I feel some of that pressure at Wyoming. I tell my dean and my provost, yes, of course I'll pull in more money for you, sir, absolutely. Then I go to my office and promptly forget that conversation ever happened, basically. My number one goal is getting students prepared for this future, for a successful future, right? So most of what I work on, or most of what my students work on, is in the exploration and discovery side. We also do feasibility studies for some companies, like is your deposit actually rich enough to make money to mine? We also do some rehabilitation stuff because that will also be hiring a lot of students in the future as mine closures. So my group currently, people directly under me are 6 grad students and 4 undergrads. This is a pretty large group by geology standards. They all work on ore deposits in Wyoming. A lot of geology profs like to go around the world. They'll work in South Africa, they'll work in Brazil, stuff like that. Wyoming pays my bills. I'm a state employee, and I feel like I should work in Wyoming as a result, right? So all these stars are places we've been working in the last year alone, right? In the last year alone. These are deposits we've been working on. Everyone works on multiple deposits. This is also unlike my colleagues who put 1 student per deposit. My students can say they worked on 4 on their resume instead of 1, right? So this is a field trip a couple weeks ago, right? They're all working on a deposit together. They're all doing different aspects of this deposit. This is in the Ferris Mountains in central Wyoming. Truck got stuck. We spent 3 hours digging it out. built some character that way, right? We're not tied to one specialty. I'm not a petrology lab. I'm not a structural geology, a fault and fold lab. Whatever the deposit needs is what we give it, right? Which is also unlike some of my colleagues, basically. So I also reach even more students via classes. This is probably more impactful, actually. I teach 1 to 2 economic geology classes per semester, which means if you're an undergraduate or a master's student, you can take up to 6 courses on ore deposits, on mining, that you can put on your resume. 6. If you're a PhD student, you could probably take up to 12 before you start repeating. Some of the ones I've offered recently, an intro level earth resources, an ore deposits class, a mineral exploration class specifically, because that's where a lot of people are going to get hired, and then various seminars on various topics, right? All of my classes are designed to impart skills that people want when they hire my students later. The number one ask I get from employers is, do you have anyone who can write? Can you have someone who can actually write me a technical report, right? Or am I going to have to spend hours editing someone's word slop, right? So I have a lot of writing in my classes. We do resource estimation, we do assays. We even do stuff like personal growth and leadership skills, resume building, that sort of thing. I want my students to improve every semester, right? I want them to get better every semester, right? So those are the skills. One course I want to highlight is this mineral exploration course. This is my flagship course. I get grad students applying to me specifically so they can take this course. And you'll see why in a second. So remember the copper problem, right? This is what's going to employ a ton of people, this exploration and discovery part. If you can find all the copper, that's probably the hardest part. Eventually, if we're really short on copper, the regulatory part will go away, as it turns out, right? But finding it's going to be hard. So instead of doing a course where I just lecture on how companies find new mineral deposits, I didn't want to do that. I didn't want to just lecture how it's done. I wanted to actually do mineral exploration. I wanted to actually physically do it with the students, right? So day 1, I walk into class and I say, welcome to mineral exploration. We're going to start a mining company. And by the end of this class, we're going to own a mine. And they all laughed at me. They thought there was like some nervous chuckling. They thought it was, what the hell is this guy doing, right? What does he think he's doing here? By the end of the hour, I talked him into it. We're going to find a mineral deposit in this class. We're going to find an actual deposit. We're going to legally stake a mining claim. Tell the federal government that we intend to mine this spot, right? And by doing that, our company that they would own would also own that property, would own that mineral deposit. That was my vision for the class, basically. There were huge legal hurdles to set this up. It took 6 months of wrangling with the legal office at Wyoming, who is strictly opposed to this. But to their credit, I talked them into it. Eventually they bought in, and once they bought in hard. And they really supported this, actually. So one of the main sticking points is that we were associated with a nonprofit, the University of Wyoming, which is not allowed to own a mining claim. Nonprofits can't legally own mining claims. So I said, okay, we're a for-profit company associated with the University of Wyoming. Well, the problem is that the University of Wyoming also cannot compete with private industry. This is another Wyoming law, right? So the university spent $50,000 in outside counsel to get this figured out. And we eventually threaded the needle. We are a for-profit company whose main mission is educational, but we're also in it for the money. Don't you worry. The kids want to make money. Let me tell you, they're really into selling whatever deposit, whatever commodity they find, or selling their claims overall, or stuff like that. So we incorporated as a real Wyoming-based LLC last year. And the students voted on the name Pokes Prospecting LLC. That logo is TBD. We haven't actually come up with a real logo yet. This company, which is solely created for this course, is the world's first and only student-owned mining company. No one else has even thought, I don't know if they've ever thought to do this, or definitely no one's been able to pull it off. I'll put it that way. It took a lot of work, a lot of meetings with lawyers. It's the world's first and only student-led mining company, and I'll tell you what that means in a slide or two. And it's the world's first and only student-run mining company, right? We're the only ones doing this. People applied to work with me solely, so not solely, hopefully, but in part so that they could be a part of this, basically. So what do I mean by student owned? If you complete my mineral exploration class, you get stock in the company, like literal stock that you could sell if you wanted to, right? I don't own any stock. I'm not in it for the money, right? Some of the students are in it for the money. I'm in it to help them learn. Any profits the company makes, if we sell a commodity, if we sell a claim to another mining company, gets split amongst the shareholders, which are the students, right? They're heavily incentivized to actually be successful because they could make real money off of being successful in their company. Student-led. The board of directors is composed of current and former students. They get elected. The only requirement is you have to have taken my class and therefore gotten stocks in the company. I am not on the board. I'm not on the board. I'm the manager, the LLC manager. I wanted to be called CEO, and the board voted not to call me CEO, right? Board members make major decisions. They make the decisions to like drop claims, to change our articles of incorporation or our operating agreement. The board could even fire me if they wanted to, and I wouldn't be able to do anything about it. I have no power in this company, right? I file the annual paperwork. I file the tax paperwork every year, and they ask me questions if they need advice on a decision they make, right? Student run is in the students choose what properties to acquire, what new places to stake. So in my class, they each have an idea. On pitch day, they each come to class with their idea, and they have to convince their fellow shareholders to vote for their idea, basically. And the winning idea is our next property that we stake. They can pick any commodity they want. They could pick gold. They could pick titanium. They could pick asbestos. Someone pitched asbestos this year. It was actually a good idea. I don't tell them what to pick. I don't tell them that's a good idea, that's a bad idea. They get to learn for themselves. They get to experience success and failure on their own, and they just ask me for advice when they feel like they need advice, right? I provide some guidance, right? This is how like the companies kind of do it, but it's up to them to figure it out, to succeed and fail on their own. Also, part of student run is they make all the exploration decisions. They have to study the geology, they have to study the techniques, and they have to figure out what geochemical methods am I going to use on this deposit? What geophysical methods am I going to use? And if they pick right and they pick successfully, they could potentially sell their claim for thousands of dollars, right? If they don't pick it right, they might not be able to prove that their claim has any value. It's up to them and their decisions, basically. So it's a very, very hands-on type of course, right? Currently, we have two properties. They picked Rock Creek, which is in the northern Medicine Bows. This one has orogenic gold. This is gold in quartz veins in the outcrop, and it has some placer gold. It's an interesting spot. We definitely found some gold. I don't know if it's enough to actually like sell the claim in the future, sort of a mixed result. This weekend, we're going to Lake Owen, which is also in the Medicine Bows, to stake the second claim, the second property, I should say. That one, they're going after titanium, vanadium, and platinum. That one's a pretty exciting one because other mining companies have already staked some there and been able to sell their claims to other mining companies. It's a very active area, actually. So that's the second half of the talk. To conclude, I'm trying to address two problems related to our ever-expanding world here. One's greater exposure to natural hazards. One's our need for more and more resources in preparing students for those futures. So for volcano monitoring, I'm trying to come up with cheaper and cheaper ways to do that, right? We have some promising early results, and the cost savings could be immense. For the critical minerals, mining's probably going to employ most of the new geologists over the next decade or so. And I need to prepare them for this new reality. Some departments aren't taking this very seriously. They're sticking to their old ways. I'm taking this very seriously, and we're taking it very seriously at Wyoming. So with that, that's my last slide, and I'll take any questions. Thank you. Yeah.
The cartoon, mineral exploration without the hammer and the receivers. Is that literally true or is that a cartoon?
John would have a lot to say about that. You want to answer that one, John?
all they need is an energy source, and for very shallow, high resolution seismic, that works.
So are you doing that like in those two claims that were?
Yeah, so last year at Rock Creek, they were looking for gold in the bedrock and gold in the sediment, basically. That's the placer claim. So there's all this sediment down there. They wanted to know, how much sediment do I have? Like, if I only have a 10 centimeters, there's not going to be much gold to find. If I have 3 meters to sift through, maybe I'll find a lot of gold in there, right? So they did this seismic line, right, to try and find the depth to bedrock, basically, the total amount of sediment, so they could try and estimate their resource, how much gold is in the sediment, right? Based on, you need the total amount to do that. So yeah, that's one of the things we actually do, right? Top right is a portable X-ray fluorescence machine. It tells you the composition of the rock. It's a little gun that just shows it on the screen. We use that too, for example. Yeah. Yes. It's a great question. Yeah, so the question was, what is the land ownership typically? So the way it legally works is you can stake a mining claim on federal land. You cannot stake it on private land. You can stake it on state land in Wyoming, but we're not allowed to do that because it's a weird conflict of interest thing. So you can basically stake national forest or BLM land. You can't stake like national parks or stuff like that. And these days, you don't literally own the land forever. You sort of have to pay rent. Every year you pay about $200 or something like that in rent. And you can keep doing the exploration. To properly mine, you need like another permit or something like that, which we haven't gotten to yet in this process. Yeah, we're still trying to estimate total sizes of resources at these properties. Yep. Yes.
To keep the claim, you actually have to prove that there's value there, that it is a viable claim.
Legally, yes, you have to prove. Yeah, so the question was, sorry, thank you for the reminder. The question was, to keep the claim, do you have to prove that there's actual value there? And the answer is yes, in some ways. You have to have something there that is worth claiming. If you just have a bunch of dirt, literally no outcrop, no rocks, no nothing, technically you're not allowed to claim it. You can't like prove that there's anything there unless you did a geophysical survey and already spent a bunch of money on it. These days, you can prove it so easily. The bar is so low, the BLM is so understaffed that practically speaking, you don't actually need to prove that there's value there. Yep. All you really need to do is what's called annual maintenance, which means you have to put in at least $100 worth of work onto every claim every year to keep the claim, basically. Which that's the value from like the 1870s. $100 was like a third of your year or something like that back then. Now $100 is, less than half a day of my time just to go visit it and make sure the posts are still up. Yeah, good question though. Great question. The question is, how many students are involved at this time? I limit it to 12 students in the class every year, right? Because I don't want the shares to get split up too fast, basically. So every year, if you haven't taken the class before, you get priority, right? If I don't fill up, then I would allow alumni, like people who had taken it before, to take it again and get a second share, right? But I limit it to 12 just so that the pool doesn't get diluted too much. Yep.
That's how many each year, but how many as a group though? How many are there?
Great question. So as a group, how many are there? I started at Wyoming last year. I'm brand new. So we had 12 last year. We have 12 this year. There'll be 12 next year and the next year. Eventually it'll grow to a pretty good group. Yeah.
Together.
Yeah. So the shares every year get split, right? We issue new shares actually. So you get diluted, but the number of properties grows, right? So the total amount you could make gets diluted every year as the shares get diluted. But these are basically lottery tickets, right? The more you have, the higher your chances of hitting it all, of getting rich at all, right? The students voted on that structure. The board voted on that structure. We thought about making a new company every year so that the shares wouldn't get diluted. And the legal office said, please, oh God, no, don't do that to us, right? But the students voted for this model anyway. Yeah.
The money come from, the students have to throw in some money to pay for
Yeah, so the question is, where does the money come from for this? The University of Wyoming fronts all of it. Fronts all of it. Our rental of geophysical equipment, right? Our rental of vehicles, all these sorts of things are all fronted by the department and by the University of Wyoming. They technically own a stake as well. If we actually sell something, the University of Wyoming will get a cut of it. That's partly why they are fine with fronting the money every year, even though I don't know if they'll ever make their money back. We'll see. Hopefully they do, right? But that's what's fronting it basically. Yeah. Question.
Students going after your course, I mean, you have waiting lists every year, sold out basically.
Yeah, the question is, how aggressively are the students going after the course? It fills up every year. And then the waiting list is more informal. People will just say, hey, if someone drops, can I get on there or something like that, right? But 12 is about the right amount, actually. It's about the right amount for our department. Yep. Mike?
So how do you select the areas to go explore? And, you know, when I think of like mining, states with big mining histories, I don't think of Wyoming. I think of Colorado,
Yeah.
Nevada, Montana. I mean, obviously we have uranium, trauma, there are resources, but it doesn't seem like the most resource-rich state for these things. Maybe I'm wrong, but how do you, you know, it's a big state, where do you go?
It's a great question. So the question was, how do we pick where to go? Why Wyoming? Wyoming is our big advantage. And the reason why is because no one thinks of Wyoming as a state for hard rock mining. So all the big companies, all the big players have not already come in and swooped up the best stuff. They have not already come in and claimed the best stuff. We have a bunch of really good deposits still sitting in the ground that the students find and claim, basically. So in the class, I make them simulate the off season, right? You work for, let's say if you're working for a mining company based in Canada, you sit around for 9 months in the office, just thinking about where to go next, right? So they have to do their research with available geologic maps, with stuff in the geology library, anything they can find online. Some of them even go into rock hounding forums and like dig deep, right? And they try and find all the background info they can to make their pitch before we actually go to the place and do the actual assays and geophysics and all that sort of stuff. So I make them sort of simulate the off season and try and figure it out online based on what info is already out there. The main thing they learn is this is hard, right? Companies spend millions of dollars looking for deposits for a reason, right? They could totally find some things. It's completely possible, in part because it's Wyoming. If we did this in Nevada, every good place they would find would have already been claimed by Newmont or some other major mining company, basically. So this is kind of why it works here. Yeah, great question. Yes. Yeah, so the question is there a map on the internet that shows where the claims are? So the Bureau of Land Management manages all the mining claims for the US. They have a viewer, they have a mapping application, like a website, where you can see all the claims that are in the US right now. There's like a layer you can turn on, you can see all the claims. It's partially like where my students pick can't be a place that's already claimed. That's not legal, right? They have to figure out what's legal, what's a legal place to claim. So the BLM has this viewer where you can see all the active claims, you can see all the closed claims, place someone claimed before and has let their claim lapse, that sort of thing. And some people use that to their advantage as well, right? So yeah, they have to figure out every little bit of it before they pitch their spot. Yeah. Question?
Try to figure out a pitch that they're going to make to the company. So they are getting support for that kind of individual work as well.
Yeah, so the question is, do the 12 students go out on their own and figure out the data to pitch, right? Some of them literally do. They have like a couple spots in mind and they'll go out in their car for a weekend, go check out their spots they have in mind and see if that's what they want to pitch. Some of them say, I have enough info from the internet. I'm going to compile that info and just pitch from there, right? If they want to go out and check out their potential property ahead of time, they can totally do that. We don't like give them an allowance for that or anything like that. It's up to them. They want to use their weekend for that, right? I don't require it at all. I make them simulate the off season where it's like too snowy to go out. You can't, right? That sort of thing, right? Even though it's September when they're doing that. Yeah. Question. That's a great question. The class overall has been about 50-50 every year. Geology at the undergrad level these days is about 50-50. And the mining industry is not what it used to be. It's a lot more women friendly than it used to be. And I get more female students applying for grad school for me than male students now, right? The actual miners themselves are predominantly male still, but the geologists, the brains of the operation, are a lot more 50-50 in terms of new hires at mines and stuff like that. Yeah. Question. Yeah, so the question was, have we secured our logo? We have secured the name and we have not gotten a proper logo yet. I threw this together for this talk. The board needs to vote on a logo, and which means we probably have to have a logo competition internally, and then the shareholders will vote on a logo. But that's probably like in the next 2 weeks or something like that. We're a little busy getting ready for this Lake Owen claiming this weekend right now. Yep. Satisfied? Maybe.
So, if you had to recommend a field for a geology graduate to go into, and people have asked me this, and I've suggested hydrology or mining for minerals. Is there anything you would add to that?
Yes, so the question was if I had to recommend a field for new students or new grads to go into in geology, what would I recommend? It depends on what they want, right? But in the end, if their goal is to get a job, I firmly believe, which you'd be surprised with some students, their goal is not necessarily to get a job, right? I think that the majority of geologists are going to get employed in this phase, exploration discovery, or closure and rehabilitation. Making a mess or cleaning it up, as I like to say. That's where most of the geologists actually get employed. At least going forward, I think that's what's going to happen. In order to solve this problem, the copper companies and the nickel companies and the cobalt companies are going to pay ridiculous salaries. They're going to pay what it takes to get the people they need to make the money and because the demand will be so high that prices will go up and all these sorts of things. I wouldn't necessarily call it the new oil in terms of hiring. It's a little difficult to predict, but it's probably the closest thing to it these days, is either finding new deposits or doing the environmental side of mining, basically. That's where I think most of our grads are going to go into. Yeah. Yeah. Should I check for Zoom? Okay, I need to find my mouse again.
Sorry.
Oh, that's it. That's okay. I need to find my mouse again. There we go. Okay. From Jennifer, the question is, do we know how many of the critical minerals are in Wyoming? That is a great question. Let me share my screen again. Come on. Here we go. If I go back to my map of Wyoming, come on. Where'd it go? We don't. We don't actually know. We know that a good chunk of them are here. The main ones that Wyoming seems to have a lot of are the rare earth elements, And if I go all the way to my beginning, to the periodic table, the rare earth elements, come on, are this row right here, this row. They're very, very essential to making a lot of high temperature stuff. We're talking engines, things like that, mostly jet engines. You can use them to make very powerful magnets. They're very, very important for the medical field and the defense industry. And Wyoming has a lot of them, like a lot of them. If all of our rare earth element deposits go online, we wouldn't need anyone else in the world anymore for the rare earth elements. That's what the state is trying to invest in, is rare earths. I have students working on rare earths right now, right? So those are ones we know we have. All the other critical mineral ones, we have some. I don't know how many necessarily, and I don't know what we have that's actually like deposit grade, for example. Some of the critical minerals are counterintuitive. Carbon is a critical mineral because via graphite. You need graphite for a lot of industrial applications. We, it turns out, have quite a few graphite deposits that are not getting mined right now, right? So, but that's a great question. I don't know exactly how many we have. I do know we have rare earths though. Next Zoom question, if they'll ever let me see the chat, is, oh yeah, does Wyoming have good rare earth mining sites? The answer is yes. If I go in a little more detail, let me find my Wyoming map in just a second. Come on. Here we go. Let me go back to screen share. I'm trying to juggle it all. Can you guys see that okay? Okay. All of these stars, let's see here. This star is a rare earth element deposit, the Halleck Creek deposit. It's one of the most promising ones in that it has a bunch of rare earths, and mining it will be extremely easy. It's basically a quarry, a glorified quarry, where you crush the stone. One of the minerals has a bunch of rare earths, you separate it out, and then it's the engineer's problem, right? There's another one up here in the Black Hills called Bear Lodge. That's another very large rare earth deposit. That one is even higher grade. It has even more rare earths in it. The problem is that ore is radioactive. That ore doesn't really look like a rock anymore. It looks more like coffee grounds because the radiation has damaged all the minerals so much. But it has a very high grade. So if you can figure out how to extract it cleanly, then it would be a very valuable deposit, right? Question.
What is it emitting?
So the question was, it's a radioactive material. What is it emitting? It's mostly alpha decay. Yeah, mostly alpha decay. I don't know the exact makeup. They don't really want me to know the exact makeup of it. They did let me take the ore home though, which was their big mistake, right? They just had it in a big oil drum, like all the coffee grounds in a big oil drum. And they're like, yeah, just put it in a Ziploc, take it home, you know? And yeah. The problem is people don't know that, right? That's kind of the problem, right? But if we get them online, currently China is our exclusive rare earth element supplier. We could get off of Chinese supply of rare earths. This is a good time to do that. I would not be surprised if China tries to sabotage both projects. That's kind of their way of doing things, right? But the feds are invested in both projects. The feds have thrown money at them, which means they're very likely to get permitted and come online eventually. Question, Mike.
I thought one of the real problems with rare earths is the refining of them. And that's why it sort of got outsourced to China, because they don't have the same concerns as we do in terms of labor and environment. Can you talk about that?
Yeah, so you got it mostly right. We used to be, come on, there we go. We used to be the main producer of rare earths in the world. The United States did. Then, I don't know why it's doing this. China started industrializing. They found large rare earth deposits in China. And they wrote to American rare earth companies and said, hey, do you want stake in our deposits, and you can show us how to mine them and refine them? You can make a lot of money doing it. So the Americans came over. We showed the Chinese how to mine and refine. And then the Chinese proceeded to nationalize every mine and kick out the Americans, right? And then the Chinese artificially subsidized the price of rare earths, said it was so low that all the American mines went out of business. China was losing money on rare earths. They were subsidizing it to put us out of business, completely out of business. They did that for long enough that not only did we go out of business, but most of our knowledge of how to refine them also went away. We had already exported all of our refining to China because they didn't have environmental regulation or human rights, right? So you could refine for way cheaper in China. So we offshored all our refining. Then they nationalized the mines, then they closed our mines. And now, after some years, they jacked the price back up. Right? So now they make a killing off rare earths and they have all the knowledge and all the technology to refine rare earths. And we've had to relearn a lot of it or steal some of it back via espionage, basically. So in the Black Hills, that company and their deposit, they're building a refinery. They're trying to build their own refinery. They're trying to redevelop rare earth element refining again. They have what's called a demonstration plant somewhere near Sundance or something like that, where they're trying to refine the ore, basically. And the feds are very, very interested in getting this back on shore, right? And getting our knowledge of how to refine rare earths there again. To the Chinese credit, they had a brilliant plan, and we fell for it. Completely fell for it, right? We were chasing the cheapest costs, the biggest dollars, and no one thought that the bait and switch was going to happen, right? This is one of the earliest baits and switches that China ever did. This is before they ever did any of this to like the tech sector. They stole all of Google's technology, that sort of thing. This was before they did any of that to them. This was like one of their first big switcheroos that they did when they were industrializing was rare earths. And it was a very smart move by them. Yeah. Does that answer your question though?
Yes.
Okay. Yeah. I think we're good. Yeah. Yeah.
So, thank you very much, Joe. Small token of
Oh,
our appreciation.
Thank
for
you.
an absolutely incredible talk. I mean, you really covered so many different topics.
Thanks.
I feel like the Q&A could probably go on till 9 o'clock, but we're not going to do that.